This is Britt Caswell with another example video. In today's video, I'm covering example 4 from lesson 6-3 in the SavvasRealize Algebra 1 textbook. The goal of today's video is to look at exponential models of decay. So another situation where we would use exponential decay. In this case, we're actually looking at a population of an animal. Alright, so this is actually how they look at whether an animal is endangered or not, which is kind of cool in my book. Not the endangerment, but calculation. So anyway, so we have a pika, which is like this little rodent. Not this rodent, this rodent. And it says, how does the decrease in the pika population for years 1 through 5 compare to the populations in the years 6 through 10? So let's start by getting an equation, right? So remember, this A in our equation, it's talking about like an initial amount. Okay, so my initial population here is 144 pikas. And then this rate is the percentage that we're changing. I'm going to have a negative rate here because I'm decreasing my population. And it's by 8%, which I'm writing as a decimal, not as a percentage. Alright, now if I clean up that formula just a little bit, 1 minus 0.08 is 0.92. So there we have it. So that is our formula, which I actually graphed, but I want to show you their calculations as well before I talk about that graph. Okay, and so what they're asking is they're asking for like the average change between the years 1 through 5 and the years 6 through 10. So what I need to do is actually calculate this by plugging in a 1, plugging in a 5, plugging in a 6, and plugging in a 10. Okay, now to kind of save us some time, I'm just going to say what those values are. All that you would do is just plug them into a calculator, right? I'd replace that with a 1 and type it in, and I'd get 132. And if I take a 5 and plug it in, I would get about 95. And if I took a 6 and plugged it in, I would get about an 87. And a 10, excuse me, little buddy. And a 10 would get me approximately 63. Okay, so now we're looking at the rate of change, right? So years 1 through 5, I'm using the slope formula to calculate this, okay? So again, my slope is my change in my y values. So it would be 95 minus 132. And it would be divided by my change in my x values from 5 years to the first year. Alright, so 95 minus 132 is negative 37, and 5 minus 1 is 4. So that is negative 9.25. So that is saying that about 9 pikas a year are dying in that first section. Now let's check out years 6 through 10. So my slope in this case, I'm going to do the 63 minus 87, because that's my change in my y value. Sorry, try to make it more obvious on my formatting real quick. And then my change in my x value, right, would be 10 minus 6. So 63 minus 87 is negative 24. 10 minus 6 is 4. So we're looking at negative 6 for our average rate of change. So check this out. So as time went on, the number of pikas that are dying per year decreased. So let's check it out on the graph here. So you can kind of see that here. So years 1 through 5 are right here, and years 6 through 10 are right here. So do you see that on the 6 through 10 it's less steep than the 1 through 5? That's what you're seeing. And it kind of makes sense since a since a percentage of the population is passing away, it would make sense that as time goes on, less and less animals are around for that percentage to impact. Okay, so now the triad is taking exponential growth and doing the same thing, but now it's kind of working the other way. Okay, so if I have my exponential growth formula, instead of a minus 0.08, now it's going to be a plus. So my equation for this triad would now be f of x equals 144 times 1.08 to the x. Okay, so let's go ahead and do those calculations. So we want f of 1, f of 5, f of 6, and f of 10. And these will all be approximations because it's a exponential. These are probably not whole numbers. I'm going to show you guys a quick way to get those numbers, okay? So clear out my stuff for my other examples. So we have 144 times 1.08 to the x. So there's our equation. And so what I'm actually going to do is I'm going to create those lines. Okay, so I'm going to try to figure out what what 1 is. So that's where x equals 1. Okay, if I zoom in a bit, that's going to help out. And what I'm looking for is where those two lines intersect. So when x is 1, my y value is 155.52. And now I'm going to do that same thing with the 5. And I'm looking for where these intercept. I get 211.58. Actually, I'm going to call it 212, and I'm going to call that 156, just to kind of keep the number of numbers that I'm working with a little shorter. Okay, so now I'm going to do that with x equals 6. I get about 229. And if x equals 10, you get about 311. Okay, and so now I'm doing these other calculations. I'm going to change colors to make it more easy to see. So years 1 through 5. Alright, so I take my change in my y value, so I'm going to do 212 minus 156 and divide it by my change in my x values. I don't know what these are off the top of my head, so I'm using a calculator to help me along. Alright, 212 minus 156 is 56, and 5 minus 1 is 4, and 56/4 is 14. So on average, between the years 1 through 5, the Pika population is increasing by 14 animals per year. So now let's check out years 6 through 10. Just using that same process. So my change in y is my 311 minus my 229. And my change in x is 10 minus 6. The bottom there, I know that's 4, but I'm using my calculator to get the last part, which is 82. And so if I take that 82 and divide it by 4, I get 20.5. So that's saying from years 6 through 10, on average, that Pika population is growing by an additional 20 animals per year. And so if I pull up this graph on Desmos, here's what it looks like. And I just want to show you. So here's 1 through 5, and here's 6 through 10. And do you see how 6 through 10 is slightly steeper than 1 through 5? that's where you could see that their population's starting to boom more. Alright, so you can even see that average rate of change on the graph. So there we have it. There's an exponential model of decay and one of growth actually as well. Until next time.